and I'll be talking about Lab 3, Black Hole and Orbits. The purpose of the lab is to find the mass of a black hole using a computational model of a star with known mass and a black hole with unknown mass. Additionally, we are to simulate a computational model of a sun, planet, and spaceship. The findings are that the mass of the black hole is approximately 9.3 times 10 to the power of 33 kilograms for part 1, and the initial velocity used for part 2 is negative 22,000 meters per second in the x direction and positive 24,400 meters per second in the y direction. Now, let's talk about some physics principles. Newton's second law. We learned from the last two labs that the rate of change in momentum is equal to the vectorial sum of forces on the body. Additionally, we can derive the velocity and position update formula from this Newton's second law. Another physics principle we need is to know the gravitational force. Fg equals to mg m1 m2 divided by r squared. The last physics principle is the parallel and perpendicular components of a force. We can split a net force into components parallel and perpendicular to the momentum vector of an object. Additionally, when an object is moving in a curved trajectory, its perpendicular force will be mv squared over the radius of the kissing circle. Let's look at the code for part 1. First, we set the initial conditions for a simulation: the gravitational constant, mass of the star, time steps, and the starting time. Next, the iterative steps of a simulation. First, we set the star's position, then we find the initial and final velocity of our current step. Then, we can calculate the initial and final momentum vectors, and the change on velocity and momentum. After that, we can calculate the change in momentum over time, which is identical to the force. We can then use this information to calculate the perpendicular and parallel components of the net force. Finally, we can calculate the black hole's mass using the gravitational force formula. Let's look at the results. So, what does this mean? The pink arrow is the net force parallel to the momentum, and the blue arrow is the net force perpendicular to the momentum. The parallel component only affects the speed of the star, while the perpendicular component only affects the change in direction of the momentum. Some sources of error are that the time between iterations is too long, causing the simulation to be inaccurate, or some rounding errors from floating point operations in Python. Now let's look at the second part. We first set the initial conditions of the simulation: the gravitational constant, the object's masses, and the variables relating to time. Additionally, the initial conditions for the moon are set. Finally, we select the ship's x and y velocity. Next, let's look at the iteration steps. We can first calculate the difference in position vectors and the forces on each object. Then we can use the velocity and position update formula to iteratively update the positions of the moon and ship. Let's look at the results. So, what if this imaginary system has a black hole, a star, a planet, and a moon? If you wanted to predict the motion of the entire system, what would we need to include in our computational model? Well, we'll have to add the black hole and the sun into the model and the interactions between all of the objects. Then, think about the interactions in a system. Would there be any dominant interactions, or would they all contribute more or less equally? Now for the second question, the dominant interaction depends on the scale of the system. If all objects are spaced right, their gravitational forces will balance out, and it will be very similar to what happens in real life. However, if the black hole were to be very close to the star system, it may dominate all other interactions, causing the system to collapse into the black hole. Some sources of error are, again, the time between iterations being too large and rounding errors. Thank you so much for listening.